So today I'm going to share my research on efficient and robust hardware for neural networks with you. So neural networks were proposed originally to simulate the synapse network in our human brain. So for example, this figure shows a very simple neural network. The computations at a neuron includes the multiplication operations with the input and weight, and also the accumulation result will add it with a BIOS and processed by a nonlinear activation function. But with the increasing depth of neural networks, massive multiplication and addition operations, or we call it micro operations, are required to be executed in neural networks. For example, in the previous year, GPT-3 is a large language model neural network. It was used in ChatGPT, consists of 96 layers with 175 billion weights. So running this large language model triggers trillions of micro operations. And training GPT, of course, consume a lot of energy consumption. This energy consumption, about 1,287 megawatt hours, is equivalent to 552 tons carbon dioxide emission, and which is also comparable to the electricity consumption of 120 years for an average US household. And inference, where a pre-trained neural networks was used to do predictions, consume even more energy consumption. So according to NVIDIA and Amazon, 80% of this energy are used for inference. So my group is trying to develop some methodologies from efficient AI algorithms and efficient hardwares to reduce energy consumption. So in this talk, I'm going to present two efficient AI algorithms, class-aware pruning and class-exclusion early exit. And also I will present some efficient methodologies to reduce the digital accelerators for neural networks like the systolic array in TPUs. And the energy consumption in accelerating neural networks majorly from the data movement by loading the weights and also the huge number of micro operations. So that to reduce the data movement, I further developed a logic-based neural network design. So after training a neural network, we embedding the weights into the circuits and optimize the circuits so that the circuits can be used for application-specific design. And we also target some in-memory computing platforms like RRAM-based crossbars. So they are in-memory computing platforms. They don't need to load the weights from the memories. They just do the computing and save the data in the memory. But they are not mature enough. They suffer from variations, so that if you do not address the variations, the accuracy of the neural networks accelerated by the crossbars will be degraded significantly. So I will present a topic on this. So let's first look at the first topic about pruning. So you might have heard of a lot of pruning techniques, but our work proposed a new pruning perspective called the class-aware pruning. So the basic concept can be seen from this figure. The basic idea is that if you use a very simple neural network to do 3 classifications, and we found that different neurons, they are important for different number of classes. So for example, this neuron is important for 3 classes. So important means that if you remove this neuron, the accuracy of those 3 classes will be reduced significantly. And this neuron is important for 2 classes, for example. And this neuron important for 1 class, and this neuron is important for non-classes. So we are wondering whether we can remove those neurons that are important for a few number of classes, so that the remained neural networks contains of neurons that are important for many, many classes. So this is our basic idea. But of course, we have to use retraining or fine-tuning to compensate the accuracy loss. So we want to apply this class-aware pruning to some more complex convolutional neural networks. So in convolutional neural networks, a neuron is a filter. So question is that how we can evaluate how many classes a filter is important to. So to address this problem, we first evaluate the importance of a filter with respect to 1 class. And then we can add the importance scores of a filter for all the classes. So for example, a filter in a convolutional neural network, if you give an image, you will generate some output activations. So that the importance of filter for one classes can be evaluated by the sensitivities of the resulting activations to the cost function. So for example, if we reset this output activation to 0, what would happen for the resulting cost functions? But this method is very time consuming because you need to do a lot of forward propagation. To simplify this process, we use the first order Taylor expansions. And then we can obtain a first order expansion approximation. And if this approximation is larger than a threshold, then we set that the activation score is 1, otherwise it's 0. But in training data site, we have a lot of images for the same class. So for example, for the cat class, we may have 1,000 images. So that for the same output activation, we need to average the importance scores for all the images that belong to the same class. So for example, in this figure, we use 10 images to evaluate the importance scores of this activation. But this filter generated many output activations forming the output feature map. So for each output activation, we can use a similar method to generate an importance score, and we use the maximum score value as the importance scores of this filter to this class. And similarly, we can evaluate the importance scores of the same filter for the other classes, like deer, horse, or airplane. So for example, this filter 1 is importance for the cat is 0.9, and for the others is illustrated here. So we can add this number together, that is 6.5, which means that generally this filter is important for 6.5 classes. So this is our basic concept. Maybe some filters are important for a few number of classes, so we can remove them according to this number. But to take advantage of this class-aware pruning, we hope that during training, we can realize we are pruning those neurons or filters. They are not important for many classes, so that we change the cost functions by adding some penalties. So we add a penalty that is called L1 regularization. We penalize the number of the weights to be 0 as much as possible, because the filter with many 0 weights are important for non-classes. And we also add a penalty called convolution orthogonality regularization. So this penalty penalizes the similarities between the filter. So we hope that the filters, they learn different features, so that they tend to be important for many classes. So this is our pruning workflow. We first train a neural network with the revised cost function, and we evaluate the importance scores of all the filters and prune those filters that are important for only a few number of classes. After that, we fine-tune the neural network and check the accuracy drop. If it is larger than a given threshold, then the pruning ends. Otherwise, we can re-evaluate the importance scores. Because the neural network has been fine-tuned so that the importance scores has been changed, so we can further prune the filters until we reach a given accuracy drop. Let's look at some experimental results. So this figure shows an example of neural network VGG16 on CFR10. So before pruning, we see that the axis shows the number of the classes. So since we are classifying CFR10, so we have 10 classes. The y-axis shows the number of these filters, which means that before pruning, you see, for example, for this layer, many filters are important for a few number of classes. So for example, a lot of filters are important for only 1 or 3 or 2 classes. And different layers have different characteristics. For example, this layer filters are important for non-classes or for many classes. But with the class-aware pruning, we find that we can shift this distribution on the right, as shown in this red color. So the pruned neural networks, the remaining filters, they are important for many classes compared to the previous version. So that distribution are shifted to the right. And this table shows some experimental results. So we tested this method on some neural networks and data site. we check that the accuracy drop is very, very slight, but the pruning ratio is very large. And with the high pruning ratio, we can reduce the number of micro operations or flops when executing neural networks. Okay, this is the first topic on pruning the neural networks to reduce the number of micro operations. Let's look at the second technique about early exit with class-exclusion for efficient inference of neural networks. So the traditional early exit is that, so for different images, some images, they are easy to be classified, so they don't need to go through to the end of the layer, and they can be classified in the intermediate layer. So for example, some easy images, so at the end of each layer, you have a classifier like a fully connected neural network. So at the first layer, you do some classifications and you check the probability. If the probability is low, that your confidence is low, you cannot make the decision. And then you go to the next layer and find that still the confidence is low. You cannot make a decision. And then at the third layer, so the probability is high, then you can make a decision that is a cat. But we found that the previous early exit, they waste the intermediate result. If you cannot make a decision, then you waste the intermediate result. And we found that the intermediate computation result can be used to exclude some classes. So for example, if you give an image that is a cat, you send it to the layer, and in the first layer, it may learn some features like eye of a cat. Then you can use these learned features to exclude that, okay, this image is definitely not a car or a trunk, right? You can exclude some classes. And after that, if you go to the second layer, then you learn more specific patterns. Then you can exclude more classes again. Then until you have only one class, this class is a target class, that is a cat. So you can exit even earlier compared to the early exit. So this is a class exclusion, using the learned features to exclude irrelevant class as much as possible or as early as possible. But to realize this class exclusion, we have to construct the class exclusion network. So we have to use individual class exclusion network for each class. So for example, we use a fully connected neural network plus sigmoid functions for class exclusion. Of course, the intermediate feature map have to be compressed to construct a fully connected neural network. And instead of using the absolute values of probabilities to exclude the class, we use relative magnitude. We find the largest probabilities and set a threshold that below the threshold you can exclude some classes. And we determine this threshold by some search algorithms. And we tested this class exclusion on some neural networks, and we found that there are slight accuracy loss, but the number of the flops or number of the micro operations can be reduced significantly. But so we check this reduction without pruning to explore the the potential of this class-aware early exit. And also these two tables shows the number of the images that can be classified in the intermediate layers. For example, here on the VGG or Sapphire, you see that none of the images can be classified in the first layer and second layer, but still we can exclude some classes in the first layer and second layer so that we can exit earlier compared to the previous early exit work. Okay, so these are two efficient algorithms, pruning and early exit with class exclusion to reduce the number of the micro operations. So let's look at some digital hardwares to reduce the energy consumption. So why do we use the digital hardware for neural networks is a systolic array in TPU. So this figure shows the major component of this systolic array. So you see that there are a lot of mic units. They construct a mic array. Each mic unit consists of a multiplier and adder, so implementing the multiplication and addition operations. So before do the computations, the weights of neural networks need to load from external DRAM to the computing unit. And then the input are streamed into the mic unit to do the computation. So the major energy consumption comes from the data movement, for example, loading weights from memories to the computing units, and the huge number of the micro operations in neural networks. So both parts lead to the huge number of energy consumption. So let's first look at one technique to reduce the energy consumption incurred by the micro operation. So as I mentioned that you need to load the weight into the mic units, and they are fixed into the mic units or kept stationary, and the different input will stream them. So this is called a weight stationary data flow in TPU. And we found that when we load a weight, for example, quantized weight into a mic unit and it keeps fixed, then we find that different quantized weights, they have different average power consumption. So as shown in this figure. How did we obtain this? So for example, when we have a weight, we fix it into the mic units and use a model sim to trigger the different types of activation and partial sum transitions, so that there are some signal switches inside of the multipliers and the adders, so that we will trigger dynamic power consumption. And for each transitions, we recorded the power consumption and we enumerate all the transitions and use the average power consumption in this figure. So in this figure, we see that with 8-bit quantization, we only have 256 type of weight values. For different weight values, we have different average power consumptions. So of course, zero, if the weight is zero, the power consumption is zero. It's not zero, it's the least, because it also have some static power consumption. It's the dynamic power consumption is zero. But we can also see that there are some weights, they have smaller power consumptions, average power consumptions compared to the other weights. So then it gives us some hints that why not we tell this information to the neural network training? Why not we force or restrict the neural network training to use those weights, values that can lead to smaller power consumptions? If we can still guarantee the accuracy, then automatically when we run a neural network on systolic array in TPUs, automatically the average power consumption can be reduced. So this is called a power-driven weight selection during training. And also we also found that different weight values, they have different timing performance. So for example, when you load a weight into the mic units, if you trigger different activation transitions, it will trigger different passes in the digital circuits. And those digital passes have different delays. So for example, for two different weight values, 64, negative 104, you see that with different activation transitions, we have different delay distributions. And we see that for different weight values, the worst case delays are quite different, which means that their timing performance of different quantized weight values are different. So we want to take advantage of this information to tell the training, please train those weights, those weights with only those values that lead to very small worst case delays. If we can still guarantee the accuracy, then if the circuit can work with the same clock frequency, then we can reduce the voltage scaling. We can apply the voltage scaling, reduce the voltage, but even though the delays of those remaining mic units increases, but still they are smaller than the clock period. So in this way, by delay-driven weight selection, we can reduce the voltage so that we can reduce the power consumption significantly. So we are so that we take advantage of this delay and power-driven weight selection to reduce the power consumption. So we see that we tested it on very large neural networks on large data set, and there are slight accuracy drop, but the power reduction is significant. And originally in the neural network training, if weights are 8 bits, they have 256 weight values, but you see that we don't need so many weight values. For example, on LearnNet 5, we only use 35 weight values. And on some efficient night, which is more than 100 layers, we only use 50 weight values so that we can reduce the power consumption significantly. But this method only reduces the power consumption incurred by the micro-operation. So what about the data movement? They still consume a lot of energy consumption. To address these problems, we developed some logic-based design of neural networks. So basic idea is that shown in this figure. So for example, we have a neuron, it have two inputs, then the inputs should be multiplied with the weights and added together and processed by activation function. So we found that in many applications, after training, the weights are fixed. They don't need to change anymore. So we can take advantage of this fixed weight to simplify the multipliers. So for example, this figure shows a 2-bit multiplier, and it has two inputs and weights. But after training, the weights are fixed. For example, W0 equal to 0 and W1 equal to 1, for example. And then we fix those values and use it to simplify the logic gates in the multipliers to do the logic optimization with some EDA tools. And we found that when the weights are fixed, the logic becomes such a smaller circuit. And in this circuit, you see that there are no weights anymore because the weights are fused or embedded in the circuits. There are only inputs and outputs, and you don't need to load weight anymore. And also the delay and the power consumption and the area of such a circuit is much, much smaller than the original multipliers. But this figure only shows a simplification of a multiplier with a simple weights. Let's look at the circuits for a neuron. So for example, we have two inputs, each input multiplied with a weight, and their weights are different and results were added together. So we use different weights to simplify a multiplier. The resulting circuits are quite different, as shown in this figure. And then these two circuits are concatenated with a full adder. And then we send it to the EDA tools for logic optimization, and the resulting simplified microunit is shown in this figure. So in this figure, it's very simple compared to the original two multipliers and one adder. Its delay is decreased, the power consumption reduced, and area is reduced. And one important thing is that you don't need to load weight from external DRAM so that it can save a lot of energy. So we apply this technique for some fully connected neural networks. For each neuron, we apply such a technique so that the whole neural network can be flattened to a combinational circuits. Then we insert flip-flops at the end of each layer so that to enhance the timing performance. And such a circuit can implement the neural networks with a very, very high throughput and low latency. And we also recognize that at different weights, they also lead to different simplifications of multipliers. So we select those weights that can lead to smaller simplified multipliers. And we train the neural network so that the resulting circuit can have a smaller area. And we apply this technique on three applications like optical fiber communication, jet substructure classification. They are all applications that require high throughput and low latency. And we compared this method with those methods just concatenate those microunits without embedding. And we found that power consumption and area overhead can be reduced significantly. So this is one technique to reduce the energy consumption incurred by the data movement. Okay, so let's move to another technique called in-memory computing with RRAM-based crossbars. So these are analog circuits. So as shown in this figure, this is the RRAM crossbar. So on the between these vertical lines and the word lines sits the RRAM cell. So electricity property of this RRAM cell is that its conductance can be programmed so that we can use this different conductance to represent different weights. So when we apply a voltage on it, it will generate current. This V times G implements the multiplication. And also if we apply a vector, a voltage vector on all the word lines, then the generated current flowing through at the bottom, accumulate at the bottom. This accumulation realizes the addition operation. So if we program this RRAM crossbar as a weight matrix and represent the input with a weight vector, voltage vector, then this crossbar can implement the matrix, weight matrix, and input vector multiplication, but in analog domain. So you don't need to load the weight from memories because the weights are represented with the conductance of RRAM cells. So this is analog in-memory computing. So it can save a lot of energy, seems very promising, but the very important problem is that such an analog device suffers from variations and noise. So you want to program it to a target conductance, but in fact you cannot because of those variations. So if cannot, then the weight will have some deviations. And if the weight has some deviations, if you use crossbars to implement some convolutional neural network, then the feature map will not be correct. And the first layer of the feature map is not correct, then the second layer, if the weight still have some variations, then this erroneous feature map will be amplified across layers until reach the last layer, but the accuracy drops significantly. So for example, according to one reference, the weight follow a log normal distribution, and we simulated this distribution, how it affects the accuracy of the neural networks. So the y-axis shows the weight variations and y shows the accuracy. You see that on large neural networks with increasing weight variations, the accuracy drops significantly. And if we do not address this problem, then the energy consumption, the energy efficiency of those analog in-memory computing cannot be taken advantage. So we have to address these variation problems. To address these problems, we first proposed the error compensation techniques. The basic idea is shown in this figure. So the basic idea is that we know that we implement those filters in convolutional neural network with RRAM crossbars, but the input of those of these convolutional operations, they are correct, and the output feature map is not correct because of these deviations in the width of those filters. So I'm wondering why not we take advantage of the correct input to correct or calibrate the erroneous output feature map. So this is our basic idea. So to achieve this, we first use average pooling to make their dimensions the same, and we concatenate them together, and then use a very simple and computing efficient generators to generate some error compensation data. And then this error compensation data will be concatenated with original erroneous output feature map, and use a compensator or corrector to calibrate, and the resulting calibration feature map, they are correct. But you see that we use some generator and compensator, but they are very computing efficient. We assume that they can be conducted in a digital domain, and we only insert a small number of generators in the early layers of neural networks. And another technique we use to address the variation is called error suppression. As I mentioned, that the error propagations across the deep layers of neural networks is amplified, but we want to suppress these average propagations across layers. So we take advantage of a mathematical methodology called elliptic constant regularization. The basic idea is that, so for example, take a layer as an example, so that the weight matrix multiplication W times X, because the weight have some variations, so we multiply it with E theta here. So because of these variations, the inputs of this layer will have some deviations. So for example, initially we assume that the nominal value of the input is X1, and because of the variations in the previous layers, the deviated input is X2. And we hope that these differences will be surprised after this layer. So this means that, for example, X1 minus X2, and the function of this layer can be evaluated by W is theta X1 plus B. So this is original, and then minus the differences here. So this means that any differences at the input of this layer will be surprised after propagating this layer if we constrain to the K smaller than 1. So in this way, if we can realize these restrictions, then we can suppress the error propagation. So to derive this, we move this on the left, And then we need to restrict the p norm of this weight matrix times the E theta, smaller or equal to K. But this is a distribution. It's difficult to realize this. So we use the 3 sigma point of this distribution, so that we have to use the p norm, restrict the p norm of this weight matrix to be smaller than value. But here is a question how we can restrict the p norm of a weight matrix during training. We solve this problem by a simple way, use 2 norm, and it's also a spectral norm, and also the maximum singular values of the matrix. And the singular values of the weight matrix are also the square roots of the eigenvalues of this W transpose and W, so that we add penalties into the neural network training. So we push the square roots of these eigenvalues of this W transpose W to be lambda as much as possible. So to balance, but we add a coefficient to balance the original training and this penalty. And with this 2 technique, we find that, okay, we apply this technique on the neural networks. If we do not use this technique when the variations is large, then the accuracy drops, for example, for this neural network to 1.69. So that does not make sense to use this analog in memory computing. But with our method, we can still enhance the accuracy of the neural networks and the variation to at least 95% of the original accuracy. But we only increase the additional generators and compensators by a small number of ways and insert only a small number of layers with such error compensation. Okay, so these are the error correction and error compensation for analog in memory computing for digital circuits. Okay, thanks for your attention. I'm looking forward for some questions and comments.
Yeah, I had a question, actually several, but I'll just go with one for now, that in the section regarding the logic-based design for neural networks.
Yeah, this one, right?
Yes, exactly. So I just want to make sure I understood that correctly. Is this essentially designing an ASIC based on weights that have already been trained? Is that what's happening here?
Yes, you can target ASIC, or you can implement the circuit on FPGA so that you can still switch the applications.
Right, okay. So a programmable circuit, essentially.
Yeah.
Okay, but the circuit structure is obviously based on the weights that have already been trained.
Yes.
I have a question about pruning, which you described in the beginning, slide 11. So pruning seems to be a viable strategy for some cases, especially for image classification. Are there cases where this doesn't work, where you see that you cannot discard any filter because somehow, in some way, filters seem to be important for all classes? Is that possible? And are these cases where the network wouldn't do a good job anyway? Or are these important classes where you say, okay, in this case, pruning just doesn't work?
Okay, I think that if a neural network is very compact and the filters are important for many, many classes, then we say that the redundancy in such a neural network is low. It might be difficult to prune such neural networks. So
with a compact network, you mean few layers or small layers?
Not necessarily few layers. So for example, in a layer, the number of filters is small and it's compact because if you remove it, it affects the accuracy of all the classes significantly. If you have such a case, then we say that such a neural network is very compact. It does not have so much redundancy.
It would be like a network that is already pruned for some reason, right? So as if you had applied pruning process before. Okay,
so you mean that we can first apply the other pruning techniques and check whether we can still have some potential to prune it. I think that is a good point. We have not explored about this, but we only compared our pruning ratio compared to the other previous work.
A similar question about early exit for classification. I mean, this seems to be something that is made for classification tasks.
Yes.
Because you could rule out certain stuff early on. But what about other deep learning workloads like segmentation or large language models? So
that is a good question.
For those?
Yeah, but for large language models, actually, we are now trying to apply this technique, but it's difficult because for the large language models, it has many output, like additionally, like about 30,000 classes, something like that. We want to construct some hierarchies. So, for example, from coarse to fine granularity to allocate some classes, they belong to a large class. And then we can exclude some large classes, then we can go to this large class and exclude some specific class again. We are trying to have some hierarchies.
May I ask something about this as well, since you're already on the slide?
Yeah.
So is the basic idea here essentially to build like almost like a side channel neural network so that each layer's output gets, somehow interpreted by a fully connected layer or something like that? Is that the main idea
for
here?
example, in a convolutional neural network, for the convolutional neural network, here you have a classifier. It's usually a fully connected neural network, right?
Right.
Yeah, you do some classifications, something like
Right.
that.
And so, I mean, you're essentially sort of adding like a side network here to interpret those intermediate, right? Okay.
But it's very small. Otherwise, it will incurs a lot of computation costs.
Right. That's what I was thinking. Okay.
So it's usually very small compared to the convolutional operations in the layers. It's very small.
Okay.
When you report on the power consumption per weight, that was on slide 23, where does the data come from? I guess that's from simulation, right?
Yes. For example, we first use model sims to extract the signal switches in the mic unit when we enumerate those activation and partial transitions. And then we use Synopsys prime power. I forgot the name of the tool. They can evaluate according to the signal switches what is the dynamic power consumption. Okay. We use some tools to extract them.
And on the next slide, which is about delay-driven weight selection. So in my world, an FMA or MAC operation always has the same latency. Okay, it's like 4 cycles or 6 cycles. But here it seems like it depends on the values. So can you?
Yeah, it depends. In fact, why you might have heard of those same latency because they are mentioned the worst case delay. And also the clock frequency is much larger than the worst case delay to give some margins in reality. But we find that it's not necessary to do this because in the neural networks, the activation transitions, the partial sums, they may have some special patterns. And if you simulate them, you find that different weights. So for example, 11111 and 1001, they have different delay distributions. These are the real data. These are the real delay distributions. But from the designer part, they don't care about those two detailed things. They just care about if you use any weight value, what is the worst case delay? But we find that for the neural network, it's very flexible to adapt the neural network to different weight values. If you push the neural network tree with only those weights with smaller delays, it's also okay.
Regarding the previous slide, actually, just right before that, I was going to ask the same question as well, Georg. I was a little bit confused as to where this data came from. So I kind of wanted to ask, one, as to whether the distribution of these quantized weight values, is that something that's kind of like random? Is there some structure to like how it comes about?
Okay. Of course, 0 is the smallest one, and the 2 to the power of n also consume some small power consumption, right? Because it's a shift operation. And we also found some other ways, I forgot which ways, because of their patterns, like 1001 something, they compared to the other weights, they also consume less power consumption.
Okay, and do you know why that is? Is that because of the size of the memory block within the?
No, because of this weight patterns, the activation transitions, they trigger different less signal switches in the digital circuits.
Okay.
Multiply by 0 or multiply by 2, that's a very simple operation.
Yeah, that's very simple, but we also observe that, but we also observe that there are also some other ways. So they are not 2 to the power of n, they are not 0, but if you do the simulations, they lead to less signal switches so that the power consumption is small.
Okay. Yeah, that's what I was wondering, if there's a structure to it, like 2 to the power of whatever, but you're saying it's not.
Of course, okay. 2 to the power, yes. But we also, like, for example, for some neural network, you select 50, it's not all 2 to the power of something. You must include some other ways, right?
There's a question in the chat. How is latency measured from slide 23? Maybe you mean 24?
Yeah, maybe 24. So still we use model sim. So it's a tool. And when you load the weight into the mic unit, you keep fixed. And then you trigger some activation transitions. And those transitions trigger some passes. that is called a dynamic timing analysis, so that we can use those dynamic timing analysis to obtain, so for each transition, what is the delay? So you can use some tools to extract them. That is called a dynamic timing analysis. And by the way, I use the open source NAND gate libraries when we construct these multipliers and adders.
Okay, can I come to slide 32 about the RRAM devices, which I find really intriguing because it's like the advent of a new era of analog computing. So how large are these devices as you can manufacture them today? How do they compare with standard logic?
Actually, they are not mature now. Most technology node IC is very old, like 45 or something. It's not very advanced because such devices, if you manufacture with very advanced technology, the yield is very low. There are a lot of faults and variations, so that they are not stable if you manufacture a large. Even you use some old technologies, they also suffer from some variations and noise and programming problems. So the device is a big problem for the analog in-memory computing.
I guess on the next slide where you cite these error rates,
yes,
weight variations. I mean, a weight variation of 0.1, which I interpret as 10%, that seems to be large, but is that a typical value, or is a typical value more like on the right of this diagram, like 50%?
Okay, I think that when we read some papers, different manufacturing technologies, they have different variations. So we simulated from 0 to 0.5, that is the worst case. So usually different manufacturing technologies follow between this range, depending on which technology you use. So we cannot determine, okay, definitely is such a value or such a value, depending on the manufacturing technology.
Okay, are there any more questions from the audience? There's one in the chat. Any FPGA network designs or your work which I can refer to?
I only implement this work on FPGA to verify that the performance, the area, and power consumption. But we don't do specific FPGA for neural networks. We use just FPGA as a validation hardware.
If I may ask one more, this is the last one that I had. It was on slide 34. Yes, I believe so. The structural error compensation. Okay. So I was wondering, is the structural error here that you're compensating for, is that coming from some imperfection within the circuit itself? So there's some there's some structured bias in terms of, like, for example, the circuit is supposed to output a particular value, a certain voltage or something, but because it's not a perfectly constructed analog circuit, that there is some bias in what it's outputting. So is this what you're fixing? Like, is that where the errors come from that you're correcting for?
Yes, the areas of this output feature map comes from the weight deviations of those filters, right? But you don't know what is the specific weight deviations in such filters. But the output is erroneous, right? You want to compensate it.
Is the weight deviating from what it should be because of a property of the circuit?
Yes, because of property of the circuit.
Okay.
You want to program it, but you cannot represent it correctly. That is a property of this analog circuit. Yeah.
Right. Okay. So as I understand it, this is essentially like a software fix for a hardware problem. Is that?
Yes.
Okay. So then my follow-up question on that would be that if the hardware itself had properties, or let's say an error that was changing based off of circumstance, like for example, the ambient temperature, that's not something that, you'd have to keep correcting for it repeatedly.
Yeah, but we assume that this generator and compensators, they are conducting in digital domain because they are very computing efficient, and we only insert a small number of such computing in the whole system.
Okay, so you can continuously correcting.
Yes.
I see. Okay, cool. Thank you.